All right, so let's say we have this theoretical rectangle here, right? And we already know that the area is going to be equal to 25, aka whatever the length is times whatever the width is, that's going to be equal to 25. And let's say I asked you to find the dimensions of this rectangle so that the perimeter, aka 2L plus 2W, or length plus width, and we want the perimeter to be as small as possible, aka we want to minimize the perimeter. How we would do that is first we gotta isolate one of the variables so that we can plug it back in to easily work with. Because working with one variable is one thing, but when it comes to a variable, it's a lot more difficult. So let's say we isolate W. Well, how we would do that is that we divide L on both sides. These would cancel out. And then 25 divided by L. So we would have left on the left side is W equals 25 over L. So let's take this variable, this isolated variable, and plug it in back to the perimeter. So now we would have 2L plus 2 times 25 over L. Let's simplify this part real quick. 2 times 25 is just 50 over L equals, and plus 2L. Now, to get this optimization, as we would call it, going, we would have to take the derivative out of this equation here, as if it was a function. It's not really a function right now. I mean, if you put f of L, that would be a function. But as what we had before, that's not really a function. But let's put a function sign there, just so that for clarity. So let's take the derivative out of this. As we know, the exponent is always an invisible 1. Power rule, we would bring this 1 to multiply into the coefficient. 1 times 2 is just 2. And then subtract 1 from the exponent, as the power rule states. 1 minus 1 is 0. Anything to the power of 0 is just 1. So what we have is just 2. As an exponent law would say, 50 over L is equal to 50 times L to the power of negative 1. Again, let's bring this down to the coefficient. So negative 1 times 50 is negative 50. If you subtract 1 to the exponent, negative 1 minus 1 is negative 2, aka this would now be negative 50 times L to the power of negative 2, or negative 50 over L squared. So what we have now is the first derivative. And now we got to do something called the first derivative test, which includes setting this derivative we have here, let's call this f prime of L, and make that set to equal to 0. 2 plus negative 50 over L squared. And because this is a negative, we can just change this plus sign to a minus sign. So how do we make this 0? Well, let's add 50 over L squared on both sides so that we have 50 over L squared equals to 2. Now let's multiply L squared on both sides so that it's on the numerator side. These guys would cancel out. Now it's just 50 over equals to 2L squared. Divide 2 on both sides. Now we have L squared equals to 50 over 2, which is equal to 25. Take the square root of both sides. Square root of L squared is just L. Square root of 25 is 5. So now we know the length is going to be equal to 5. And let's plug this back into the original area equation so that we know what the width is. You can choose either L times W equals 25 or W equals 25 over L. It really doesn't matter because it's the same process anyway. This comes from here, so it works the same anyway. So let's do W equals 25 over L. W equals 25 over L. L is 5, and 25 divided by 5 is just 5. So if you wanted to get a perimeter as small as we can, the dimensions of this rectangle would actually be 5 by 5. So that means that the perimeter, when it's as small as it can be, the rectangle is not just a rectangle, it's also a square. Now, we solved that, but why does this work? Why does this turn out to be the smallest using the process that we have? Well, like I said, this is derivative, right? and this is a function. Now, whatever this function looks like, the derivative describes the slopes of this function. So if I plugged a number here, whatever number it gets is the slope at that point. So if I plugged in 1 as L, and whatever that number gets out of the derivative, that's the slope of this function at 1. And what's fun about that is that when the derivative, when you plug in a number and a number that comes out of the derivative is negative, it's always going to be decreasing. And if the number that comes out of the derivative is positive, it's increasing. And what we can tell from that is that when a number is decreasing and then increasing at a point, which is why we put 0, that's called the critical point, when it's decreasing to increasing or to increasing to decreasing, this is what we call the extrema, or a minimum and maximum. That's how we can find a smallest perimeter possible, because that's the minimum perimeter or the maximum perimeter. So let's see if our original statement of smallest perimeter is even valid to begin with. So what I like to do is just draw a line and put all the critical points, which is just 5, and then try to find a point below 5 and above 5 to see if it's decreasing and then increasing. Because 5 is the critical point, it's either going to be a maximum or minimum, or sometimes neither. So, and if it's a minimum, then it would turn out to be negative slope, which is decreasing, and then positive slope, increasing. But we got to see if that's actually true. So let's pick a number below 5. Let's say, we can't pick 0 because that'll be undefined. Let's pick 1. Let's pick 1. And above 5, let's pick 10. So let's plug this into 2 plus negative 50 over L squared. Or, like I said before, minus. All right, this is the derivative, just to make sure. So 2 minus 50 over 1 squared, which is just 1, that'll be 2 minus 50, which is negative 48, which you don't have to evaluate as long as you know that it's going to be negative, which, like I said before, is decreasing. Now, let's plug 10 in. That's going to be 2 minus 50 over 10 squared. 10 squared is just 100, so that's going to be 50 over 100, which is equal to 1/2. 50 over 100 is equal to 1/2. That's equal to 1 1/2, which, as long as you know it's going to be positive, you don't have to completely evaluate it. So, because this is decreasing and up until 5, and then after 5 increasing, we know is that that's going to be a minimum. And that's how we know that the smallest perimeter possible, the dimensions would be 5 by 5. And I forgot to actually evaluate the perimeter, so let's do that real quick. So 2L plus 2W, let's do it over here. We know the length is equal to 5 plus the 2 times the width, which we already know is 5 again. 2 times 5 is 10, plus 2 times 5 is also 10. The perimeter is 20. So the dimensions to make the smallest perimeter is 5 by 5, and the smallest perimeter for a rectangle with the area 25 is 20.